All right, we're back, Mr. Ben.
Looking kind of orange today, Mr. Z.
Yeah, you too, Mr. Ben. Why are we wearing orange again?
I think it's to show that we're going to stand up against bullying.
That's right. That's right. We are standing up against bullying. Okay, we're back for another video here. We're in our third video for earthquakes. So let's take a look at some of these learning outcomes. First one there, you should be able to explain the nature of seismic waves and their importance in determining Earth's structure. Because, you know, we can't dig all the way down there and see what's going on, right?
So we have to figure out what's in there from, like, the waves that we send down there. Kind of like an ultrasound, like, I had daughters before they were done because of the ultrasound.
Yeah, I did too.
So
exactly.
So it's kind of like that on the Earth.
Yeah, and then you should be able to explain the motion and speed of P and S and surface waves. All right, and then also how they're affected by that, by the interior structure of the Earth.
So depending what they go through, that's going to change how they move.
Exactly.
Okay.
Exactly. And then finally, I can describe elastic rebound and the accumulation of strain in rocks.
It was kind of like, I think when Mr. Baldwin was talking about bending the piece of wood with Mr. Wad, and then, you know, kind of snaps back instead of breaking.
Yeah, exactly. Exactly.
All right.
All right, so let's get started. All right, this is a pretty interesting diagram here, Mr. Ben. Looks really complicated.
Okay, well, I think we can look at a general appearance overall, and then we'll go to the real close specifics. So we're looking as we go to the right. That's the velocity is getting faster, right?
Yeah, I see that.
Okay, and then this is like going down in the Earth.
Depth. Right,
okay.
I got it. Kilometers.
So looking at this wave right here, the primary wave, it looks in general, there's a pattern that as you're going down in the Earth, it looks like you're shifting to the right. So
and it's getting faster, it looks like, right?
Yeah, so it looks like maybe as you go down in the Earth, it's more compact and dense there, isn't it?
Yeah, it is.
Okay, so it looks like as it gets more dense, maybe your speed is kind of increasing. But then it looks like it gets to these points or these divisions, like the mantle and the outer core, it like puts on the brakes, big change in speed, because when you have a flat line, you are still, I guess from physics, you are still at this, you're changing velocity, but you're not changing depth. So all of a sudden, could this be like how they figure out where the different boundaries are on the Earth?
Yeah.
So a big change in speed between here and here says, ooh, you ran into something in there that doesn't allow you to go through as quickly, maybe.
Yeah, or something changes. Its characteristics change.
Okay. And then like this one over here, we get to the outer core, and then it puts on the brakes, and it doesn't show up again.
Yeah, it just kind of disappears, huh? Well, maybe that'll be a little bit clearer in some of the slides to come.
Yeah, well, let's look at the blow-up over here.
Let's look at that one.
So that's like a big blow-up of more like where we've been in the Earth.
Yeah.
So starting from the surface down, it looks like as you go down, it gets more dense. Looks like the speed is increasing. And then you get to the dotted line there, you get to a depth in the Earth. It looks like we're about 30 kilometers down.
Yeah.
And then all of a sudden there's a change. And then your line becomes more steep, so that would mean your speed does what? It becomes more...
Well, we're still shifting a little bit more to the right, so we're increasing. All right.
Okay, so you've got a steep line, so you're increasing speed, and then it looks like it puts on the brakes kind of right there between the lithosphere and the asthenosphere. Yeah. Maybe it hits something that allows it to slow down, like maybe a liquidy layer.
Maybe.
Or something down there that doesn't allow it to go as fast. So it goes slower, and then it looks like it kind of picks up again. But I think what the key is, wherever you see a little jog in the line or a shift, that means that either one of two things, like the composition of the rocks are different, or the material must be somehow different for it to change speeds.
Yeah, maybe it's the phase of the material.
Oh, that could
be different.
Like if you are driving in the winter and your car's hit like a big puddle, your car kind of slows down a lot because you're going into liquid instead of solid.
In a different phase.
Hey, that could be it. Oh, that's leading right into this slide right here. So the velocity of seismic waves depends on what? You said the phase?
Yeah, I thought the phase. The phase and then maybe the density of the material. So if the density changes, maybe the speed will be affected by it. And then if the phase changes, so if we're going from solid to liquid or semi-solid, then that may have an effect on the velocity of the wave as well. So we'll say phase and density there.
like in the cowboy movies in the old days, they put their ear on the train track because they can hear the train from further away. The sound comes quicker through the solid rail, solid material, more dense than the air.
Yeah, you're right. That's a really good analogy there.
And then it says P and S waves travel faster through, I just kind of said it, through
through solid.
Like the rails, through more solid material than they do through like a more liquid or a spread out material.
Yeah, exactly. All right, so does granite or periodite transmit faster seismic waves, and why? I don't know. We've seen, I think we talked a little bit about granite. Actually, we just talked about it, I did a little bit in my class this week when we were talking about some of the geologic structures out west, some of the batholiths and things like
the
that.
type of mountains,
during mountain structure this week. But periodite, I haven't heard that one. I don't think we've talked about that.
I think that's a really iron-rich mineral that's more like way down, like at the mantle base.
Yeah, you're right. That's exactly where it's at.
So if it's more iron and way down at the base of the mantle, it'd be more compact.
Yeah, and I would say it's probably more dense.
Yeah,
than something like granite.
So more dense, like iron, like the rails of the train track.
Yeah.
Probably faster through that.
Yeah, it could be. It could be. So, so our question here is: does granite or periodite transmit faster seismic waves? So, if something that's made of iron that is more dense, right? It's probably going to transmit those waves faster than would granite, which is less dense and more silica based.
So if the particles are further apart, it's kind of like that game Pass It On, where you pass it on. It takes longer to pass it on when you're further away.
Yeah.
But if you're closer, you can pass it on a lot quicker.
Yeah, that's right. Exactly.
The closer the particles are together, the faster it can move.
Yeah, that makes a lot of sense.
Okay, so they should think about phase and density when they answer this question.
Yeah, definitely.
Okay.
All right. So here, wow, there's a lot of stuff going on here, Mr. Ben. Looks like we've got a whole bunch of different layers here, and they actually mention density in here. We've got the mantle here, high density. We also have the crust here, which is low density.
So the mineral you were talking about is closer to this density versus the density of the crust is more closer to like the 2.7.
Yeah, definitely.
Okay, so that would definitely be a lot more dense, so that should be able to transmit it a lot faster.
Yeah, so this is where the periodite would be, and then this is where the granite would be. So if we think about the waves, seismic waves traveling through here, we know that they're going to change speed because the density of the material is also changing.
Okay. So as you go from the crust, basically a general pattern you're going to see, speed is going to increase as you go deeper and deeper. Until we get to, we saw on that other layer, now you're going to get into like liquid. Now your composition will change. Like I said, when you hit the water with your car, it kind of slows you down.
Yeah.
So that water may slow down those waves.
Yeah.
Maybe we should see on the next slide if it in fact does that. Ooh, base group challenge. They're going to do this in class,
Yeah,
aren't
we
they?
are going to do this in class. So which group can work together the fastest to depict how P and S waves move through a solid by looking at that picture? And that picture is a pretty big clue there, don't you think?
I think so. That'll be a fun one tomorrow when all the groups get together. And if a group really plans it out, they could almost have their answer before they came to class, so they can win.
Definitely.
That's bragging rights there.
Yeah, some demon dollars maybe.
Could be. All right, P and S waves. P and S waves are known as body waves. So another name for them are body waves. That could be because they travel kind of through the body of the Earth.
Yeah, I think so. I think that sounds right. And then S waves do not travel through liquids. All right, so we have in parentheses there the outer core. Why or why not? So let's take a look at this diagram here. So we've got something that says epicenter right here, and we've got focus that's over there. And I think, have we already defined those two?
I'm not sure, but
No.
basically
All right.
your energy is released from the focus.
Yeah,
and the
exactly.
epicenter is the spot on top.
Yeah,
So
exactly.
basically the energy comes from here, and it looks like it travels out in all directions, and you'd expect it to show up and be detected at these places.
Yeah, so like we talked about in a couple of videos ago, or 2 videos ago, where we said that if we throw this pebble or this rock into a pond, and we have energy kind of radiating out in all directions. And that's kind of where, if we thought about this as, this is where that rock hit that pond, and these are these energy waves traveling through the Earth itself. All right, so let's take a look at these different waves where we want to
We'll
start.
look over here, because over here it looks like, okay, that's a general, and we're going to talk about why there doesn't seem to be anything there at other slides. Look over here, we see those same pattern there and there, but now we see some other things going on right here. So it looks like when this wave comes through, the next one, instead of having that same pattern, it looks like it kind of changes direction. Kind of like if I'm driving down the road and I hit that puddle, my car kind of like turns and changes, or if I run my tires in the berm on the side, it changes my direction.
Yeah.
And then it looks like as I exit, then it kind of changes my direction again.
And what waves are these, Mr. Ben?
Well, these that go all the way through, these are those S waves. But the ones that can actually go all the way through the Earth, those would be like the number one waves, the number one quarterback, it's what primary, isn't
primary
it?
or the P wave,
Yeah.
exactly. So we can see here that these waves, as they hit the different medium, we'll call that, right, they're starting to change direction, right, which we're going to get into in the next video, like what exactly that is, right, and then they're also going to change speed, so they're not traveling in this kind of nice smooth line as they were over here in the mantle, so they are changing.
So just like if your car went into the shoulder on the side of the road, you not only would feel the car pulling, but you'd notice your speedometer changed as well.
Yeah.
So same kind of effect.
Yeah, definitely.
Okay,
All
next
right.
one. Okay, these look like ocean waves, kind of, don't they?
Yeah, kind of, they do. It's a Raleigh wave up there, and then we've got a love wave. Oh, but I don't think there's any love coming from that wave.
No, I don't think so.
Yeah,
You would
definitely.
not feel the love at all. if
Yeah,
that was
that's for
hitting
sure.
you. All right. What happens to these waves with increasing depth into the Earth? I think we said as they go into the Earth and the material becomes more compact,
Yeah.
they would go faster, right?
Yeah, because we would be standing closer together, right?
Mhm.
Like
Right.
all the molecules and stuff are real close together, so it's easier to transport energy from one molecule to another. So the more dense it is, the easier or the faster energy can travel through.
And also, if it was an easier material, the waves are going to be really kind of, they're going to have these really high amplitudes. But if you have to get the wave through something like really compact, it's probably really tough to push it up and push it down.
Yeah.
So as it goes through more dense stuff, the wave's going to get smaller and smaller amplitude, but then they'd be more frequent. You'd
Yeah,
pack
so it's
them
going to
in.
go like up and down really, really quick.
Faster then,
Yeah,
right?
faster.
So frequency is faster, and the wave, the amplitude shrinks.
Exactly.
That makes sense if it's going through harder stuff to push up and down.
Yep.
Good. So what does this really look like? Okay, so these are kind of like when the water, you said, goes into a pond and kind of the waves kind of bounce off of things. That's what that looks like. And these look like the names of earthquake stations.
Mm-hmm.
So if you had an earthquake that was here, you'd expect these stations to pick up the earthquakes at a certain time.
Exactly.
Okay, and if all the material in the Earth was exactly the same, if you knew the distance, you should really easily be able to figure out when it should show up, right?
Mm-hmm.
Well, when they did this, they found out that the waves don't show up
Yeah.
exactly when they expect. And sometimes
Yeah.
they show up, at a further station, actually before closer ones. And they had to think, how could that be? And so then they realized, it's kind of going down, dropping into a layer where it's more compact.
Sure.
And what would happen to the speed down there?
Well, it would go faster because it's more dense, and then it would come back maybe out over here and slow down again. So that could have a definite impact on the time that the seismic station actually received the wave itself. And that's kind of what this is up here, and it may be a little bit tough to see, but you can see these kind of like squiggly lines, all right, and that's the seismogram. And that's what's detecting the actual, or the seismograph is detecting the actual seismic wave.
So this is how they actually find out what's inside the Earth, by finding out how long it takes the earthquake waves to get to those different locations.
Yeah.
So kind of like you have property in the city, and you could get there by side streets or the highway, right?
Sure.
Even though the highway's longer, so even though going into the Earth and coming back out might be longer, if on the highway you can speed up more,
Sure.
by the time you pop out, you might show up quicker than if you took just surface streets going slower.
Yeah, exactly.
So that must be how they do it.
That's a really good way to look at it, Mr. Ben.
Earthquakes and plate boundaries. Hey, those black dots, they look like volcano locations, but they also outline something else.
I think they outlined the plates from last unit.
Yeah, like the Nazca plate, which is going under South America, right?
Yeah, and we can see the Pacific plate, and
Mhm.
we can see the North American plate and the Eurasian plate.
In the Indo-Australian plate over here?
Yeah, in the Indian plate. So, and this is something that we already know about. We know what's going on at those plate boundaries, and we've already actually looked at earthquake data and compared them to where the plate boundaries are. So this really isn't anything new information here. So we should just kind of a recap, I guess, of plate boundaries and earthquakes.
Noticing that, that they do match up. Good. I think we got this.
I think we do too. So let's see what the mastery check is. So review slides 13 through 17. And remember, there's a slide in there that's asking you and your group to do something. So make sure you get back to that. We're asking you to write a brief story from the perspective of a P or S wave.
Oh, interesting.
In your story, discuss things that you do as a wave that the other type of wave can or cannot do.
Sounds like that primary wave is going to be bragging.
Yeah, definitely. I think so. For example, an S wave could write about how he is jealous because the P wave gets to have all the fun traveling through liquids. All right, so good luck with that mastery check, and we will see you soon.
They should just keep this to S and P waves, not Raleigh and Love waves.
No.
Not too complicated.
Yeah, exactly. All right, thank you.